Okay, so Garrett Hardin, ecologist, responsible for the phrase "tragedy of the commons." Wrote extensively on ecological issues and the pressures of population on the environment. He's got a quote here: "Thinking about a commons problem, freedom in commons brings ruin to all." Okay, so I have a couple of administrative things I want to do before we begin. I'm having a day full of obstacles because this chalk won't erase. The previous class somehow used non-erasable chalk. Bear with me for just a moment here. I'll try to. Yeah, that's not a bad idea. Let me try that. Yeah, that's better. Okay, so administrative items include the return of problem set 8. Let me quickly put up the distribution of scores for that. So the mean score for problem set 8 involved a score of 88%. Median was 96%. The standard deviation was 18%. The distribution of grades here of various sorts of A's, there were 53. Of B's, there were 15. Of C's, there were 8. Of D's, 2. And of F's, 7. Okay, so that's the distribution of the scores. Congratulations to the majority of you who did well on this exam, or on this problem set, pardon me. The other administrative thing I'd like to do, I'd like to mention, oh dear. That's really exciting. Let me, okay, I'm gonna, no. Okay, bear with me for a little bit while things hopefully bring themselves back together. A couple of administrative things aside from the problem set. This is the last class we'll have before Thanksgiving break. I'm sure you're probably mostly aware of that. We'll have a couple lectures following the break. The plan for the rest of the semester is to discuss externalities and ways to address them, so we're going to turn our attention to that topic today. The little sort of lottery we just did a moment ago is pretty transparently meant to illustrate one sort of problem, one sort of externality, if you will. Any thoughts about the nature of the externality there? Yes. That's good. So there's this is a case where there's an externality. For every entry each one of you puts, there's a private gain. It increases the probability of winning the prize. But there's also an externality because it decreases the expected prize for the entire class. And yes, Scott. Depending on your attributes. Yeah, that's right. So maybe I can take a quick poll. So how many people? Should I do this? Let's see. How many people put down a single? How many put down a single entry? Okay, so many of you. Oh yeah, you may. No, that's fine. And how many put down? So those are ones. And how many people put down? That was a lot of you. How many put down? Okay, so how many put down more than 10? Yeah. Yeah. So what do you think the? Yes, Katie. Yeah, more or less. It was meant to be a quick illustration of the tragedy of the commons. So yes, Luke. I'll try to clarify the language on that. How many people put 0 or thought about doing it? Yeah. How many? Okay, so I'll check. I think I do say something about a positive integer there, which seems to rule out 0. Hold on. Maybe that's a defect in the rules. Okay. All right. So let's think for. I'm going to go ahead and think. Well, what on earth is going on with my computer? I don't know. Okay. So. Okay, better? All right, so let me go ahead and work quickly through the problem that I imagine you folks were trying to solve when you were going about tackling this lottery. So what was the, let's think about the nature of the maximization problem you were individually facing. So there's something we're maximizing, or at least let's suppose that that's the case. So what's the object you suppose you were maximizing? Yeah, something like this. Let's say the expected payoff from the lottery. So one of two things can happen for you individually. With the probability of P, you can win the lottery. Or with probability 1 minus P, you can lose the lottery. Okay, now for each one of you, the sort of trick in the lottery is you have a lot of control over what P is. So that's part of the trick of the lottery, because P is exactly proportional to the number of times you enter. So let's do two things. Let's let n bar be the total entries for everyone else. Okay, so we're going to regard that as just a number. You're sitting here quietly filling out your sheet. You don't have any control over what anybody else is putting. So you can't really regard n bar as a choice object when you're solving this problem. So n bar is going to be the quantity we'll think about everybody else entering. And let n be your total entries. Okay, and so you have control, as I said, over the probability of your winning P. What's the probability of your winning? Yes. Very good. So it's the number of entries you make divided by the total number of entries everybody else makes, but then also plus the total you choose, which is n. So that's the probability you win. Okay, so now that's what P is equal to. So let's think about maximizing this thing by choosing n. We're going to substitute in this probability. So this is n divided by n bar plus n. Yes? It's the entries for everyone, I'm sorry, everyone else. Everyone else. Thank you. So this is the probability for winning. If you win, what do you get? You get the total prize of 1,000 divided by the total number of entries, n bar plus n. So that's the total thing you can win times the probability of your winning it. And then if you don't win, what's your payoff? 0. So we could write this out and we have 1 minus p times 0, but that's just 0. So this is the object that you're going to think about maximizing. Is that set up clear? Okay. All right, so I'm going to rewrite this a little bit just to make it a little more convenient here. So what we'll have is max of $1,000. I'm just going to rearrange this stuff. Times n divided by n bar plus n squared. So the squared term here in the denominator. All right. Let's see. So here's what we want to do. We want to choose n. So let's go ahead and get some first order conditions for this thing. So the first order conditions, taking the derivative of this thing with respect to n, gives us a couple pieces. We need to use the quotient rule, I guess. We can write it this way. N bar plus n quantity squared minus 2 times n all over n bar plus n, did I have this right? This quantity cubed. Okay, that looks right. So at our optimum, it's going to be equal to this. And a couple of these square terms cancel out. So this implies that we'll have 1 equal to 2n divided by n bar plus n. Is everyone happy with this so far? Okay, so I'm going to just multiply this to the other side now. This implies that n bar, moving this to the other side, n bar plus n is going to be equal to 2n. That implies subtracting n from both sides, so we're going to choose n equal to n bar. Okay, so that's the optimal solution, taking as given the entries of everyone else in the class. Okay, so is the decision rule clear? So if you thought, for example, and I'm not going to try to justify this thinking, but if you thought that the total number of entries that everyone else was going to submit was 50, how many entries should you enter? 50. But of course, everyone else in the room should know that they should choose a number equal to the total of everybody else in the room. So that's now at least 100. But since you know that they know that the total number of entries should be 100, you should say yours equal to 100, not 50, and so on. So there's only one possible equilibrium here. What is it? Yeah, to choose an infinite number of entries. So everyone, that's the only way. Between this equation and the requirement that we sum over everyone in the room, if there's all of you in a room, if we sum over this, make this equal to n bar. The only possible solution to this is to have all of these things be equal to plus infinity. So that's the solution. Does anyone want to confess to choosing something close to infinity? What do you got? Did you choose infinity? Yeah. Okay. Okay. Anyone can beat that Google divided by 10? That's not really big. That's not close to infinity. Okay. All right. Anyway, so back to Garrett Hardin's dictum. Freedom in the commons brings ruin to all. So if there's a single entry of 10 to the 99, I know my payouts for $1,000 divided by this stat is going to be something too small to turn into cents. Okay. All right. So let's see if my computer is working now. It's not. This is totally screwed up. I'm going to have to be old school about this and get rid of the projector, I think, which would work better if I had chalkboards I could draw on. Let me see what I can do. Okay. So this is the yeah, it's like a bad trick, isn't it? Okay, so I want to consider another example involving not a common exactly in this case, but another externality. So this is a classic example involving a steel mill, but I think I started discussing last time perhaps. So there's a couple basic points about the steel mill. Yeah, ignore that stuff, please. So here's the steel mill. I'm going to call this example steel and smoke. Okay, so the idea is there's a steel mill, and it uses iron and coal as inputs, produces steel and a bunch of air pollution. So the basic setup here is that for every unit of steel, also produces air pollution, which is bad for the test and social costs. A general point about this is that, in general, we're going to imagine that the steel firm, doesn't face costs from pollution. And if it has a real social cost, because they're not taking those into account, it will follow that they'll produce too much steel. They'll produce too much steel and too much smoke relative to the social optimum. And so here's a picture of how we want to think about this problem. There's an arrangement here. We're going to have output Y of steel. There will be some social demand, the demand curve for steel. There's also a supply. There's a private supply curve, which is just the firm's marginal costs. So this is the supply of steel, but only taking into account the private cost of producing that steel. So we might call this the private costs of production. Okay. All right. Now, in addition to that, though, as the firm produces more steel, so this Y is steel output, it also produces more pollution, and that's not a good, but a bad. And the more it produces, the worse it is. So this will be you can think of this as the social demand for pollution. So the key thing to note about it, it's downward sloping like a lot of good demand curves. In this case, but it's negative. This is 0. So social demand for pollution is negative. It's a bad, not a good. Okay, now graphically, we can think about solving this problem just by doing a trick we talked about last time, which is to do a vertical summation of the different supply schedules we have up here. So we can do that again just by adding this to this. If we do that, let's see how I make out. We'll have a supply curve for steel that looks something like this. So this is, if you like, demand for steel and smoke. And it's this curve that reflects the sort of total social demand for the production of steel, given that there's also this joint production of air pollution. Yes? Y-axis, I'm sorry, yeah, good question. This is the price, just the price of steel. Okay. So let me go through the usual rigmarole with this graph. The firm, if it only faces its own private cost of production, is going to choose a level of production for steel, which I'll call Y sub S here. That, however, involves not only the production of this amount of steel, but also this amount of pollution, or harm, I should say harm from pollution. Let's do it this way. So this is denominated in dollars again. We add those things up to get the sort of total social demand for these things. That gives us a point here. So this is, let's call it Y star. This is the amount of production of steel and smoke that's socially optimal. So we don't want to, given that there's this joint production between steel and air pollution, we don't want to set, we could eliminate air pollution by producing no steel, but this is a trade-off that society may be collectively willing to make. But this private solution doesn't make that trade-off at all. It just produces as much steel as is profitable for the steel company without taking into account the costs associated with the air pollution. Once we take that into account, we retrieve a socially optimal level of steel production here at Y star. Okay. Yes? Oh, it's getting. It doesn't have to. It takes lots of shapes. You should think of this as the marginal damage from additional steel production. And the way I do it, I'm making that damage get larger as we get more and more air pollution. I don't know if that's the. There's nothing that this one doesn't have to be downward sloping. It could be flat. If there was decreasing marginal cost to having a lot of air pollution, it could go up. In fact, this is just an accident way I drew it. This demand curve probably needs to be sloping downward. The supply curve certainly needs to be sloping upward. The way I drew this is an accident. Okay. All right. So that's the example, or the pictorial version of the example. Let me go through a little algebra to work through this case, for a particular case with an actual production function, and so on. So we're staying with steel and smoke. I'm going to, instead of sketching a demand schedule and so on, I'm going to give you a firm production function and work this thing out more explicitly. Okay, so let's let the firm's production function involve production of steel. I'm going to call this output Y. It's going to be equal to 2 times the square root of S. And so S is the input for the steel firm. So I think of it as I don't know, iron or something like that. So this is the input. We produce output Y. The firm's problem for maximizing profits is going to be to choose how much of its input to produce. It's going to get a price for steel, which is P. Then P times square root of S. This is its total production. So this P times Y is equal to its total revenues. It's going to be a cost, a marginal cost C, for every unit of input S it purchases. And so these are its total costs. And so this expression gives us the steel firm's profits. Okay, and the choice variable is just the amount of steel or the amount of S to use to produce steel. Okay, clear? Okay, so this is the firm's private problem. Notice that there's nothing about pollution up here right now. It only cares about the revenue it gets from producing steel and the costs of that production. So we'll call this the private problem. Okay, first order conditions here. We're going to choose S. What's the first order condition look like? Well, that shows up here. Yeah, so it'll be S to the, we'll get a 1/2 times S to the minus. Okay, good. So we'll have P over the square root of S minus C, and that'll be equal to 0. Okay, so that's the first order condition for the firm. That implies pretty immediately that the level of input it chooses, which I'm going to call S sub P, so this is the private level of input, is going to be equal to P divided by C, this quantity squared. So I just scooped stuff around here and squared things. So this is going to give us the private level of input that the firm will choose. And then just using the production function, that implies that what I'll call Y sub P, the private level of output, is going to be equal to 2 times P divided by C. So this is the solution to the private problem. So I'll call this the private solution. Okay, so this is the setup. This implies, of course, if we think about the inverse of this, this implies that P will be equal to YP times C divided by 2. So this is the inverse supply function. So I'll just draw that for you now. So we have Y, we have P, and the private supply is something like this. It's C over 2 divided by Y. This is private supply. And of course, from working with the firm, this is really just another way to write the firm's marginal cost function. Okay, is everyone happy with that? Now, at the same time, we're going to assume that there's a cost that society bears. So we have this private problem. Let's suppose that it's also the case that there's a social problem. So the social problem is this. Let's let there be n people. Each person suffers total harm phi times y when y units of steel are produced. Okay, so is that clear? So there's a social cost associated with poor respiration or dirty laundry or greenhouse gases or something associated with steel production. And so there's some harm associated with this as well. The slope of this thing